Okay, let me share again. No. Yes. So now then, let me take the log transformation. So I suggest to you take the log function. That's because of the extreme value. You know, the log transformation means when we have a, you know, the log function is looks like this. I mean, it looks like this one, right? It's at the end when we have a bigger value, it's just constant. We can make just a constant because the log function is looks like this. So when we take the log transformation, then picture is looks like this. So somehow we take care of the constant variation. Is can you see the it's kind of the same band. The overall is the band one, even though we have a little bit is peak here, but it's most of them is it's the same the band, right? So take the log transformation, then it's a little bit, it's not this one, but it's that we take care of the peak one. But the problem is sometimes getting down and sometimes getting up. There's some patterns, right? You know, simply we can make the white noise, then we have to make the mean 0, 1. So do you remember the plot with the white noise? It's just the is the up and down and up and down is a IID normal distribution is mean equal 0 and with the band like that one. So now it's not only take the log transformation, it's but also just to take the difference. See, then now, yeah, it's roughly we can make um, the white looks like the white noise, but it's not yet. But now simply we just take the log transformation for the constant band, the constant standard deviation, and also it is not the up and down, and simply just to take the difference with the neighbors is today and yesterday and today and tomorrow. Then simply we can make the this kind of plot, and now the difference is the plus and minus 1 or a little bit more. But anyway, simply at the beginning, we take care of the transformation. It looks like the white noise, but I think it's not yet. It is not exactly white noise. So in this example, we take the log transformation and then take the difference. So that is the first part of the example, and there's a description and in the homework number 14. So please read the problem is carefully. Okay, so please understand why we have to take the log transformation and the difference one. So now currently it looks good. So we are going to take the two functions, it's log and the difference one. And now let me make the ACF and PACF. So ACF2, using the function of ACF2, then we can make the ACF and PACF is together. So in this case, the PACF is decreasing, the exponentially is increasing or decreasing, whatever. It's a tails off, right? So it is a tails off, and the A shift is cut off at 1. So what was the pattern? It's a cut off in A shift and tails off in PA shift. What was it? When I look at the table, yeah, to remember the table, in this case, we suspect the MA model. Okay, so you know, when we are using the ACF2 function, then is not only the picture but also it gives us the numbers, the correlation numbers and the PA shift numbers, the values, right? But it is the plot. So let me suspect the MA1 model, okay? So now I'm trying to using the ARIMA function. It's an ARIMA function. I'm using the difference and the log transformation of the data, and the order is equal to I wanna fit the MA1 model, so 0, 0, and 1. So the very first one for the P is how many parameters in AR part, and in the middle, this one is the difference. It's how many times the difference, but it's already we apply the function of the difference. So we have to say just 0, because we don't have to take the difference anymore. Let me try using the second parameter is later, but now we use the function of the diff to take the difference before. So we have to plug the 0 here, so no more difference. And let me say the no mean. Include mean is a false. If you didn't put this option, is include that mean, then in the output you can see that another estimation of the intercept, the constant. So now I just put only the MA1. It's only one MA parameter. It is the negative 0.705. I think, see, can you see that? This one is a negative one. It's a negative correlation with the neighbors. So because of that, the slope for the parameter MA is a negative 0.77. And the standard error is a 0.0341. And here is a no constant, right? And let me try again. Let me delete the difference function. Then now I have to plug the 1 here, because the second parameter, it is a number of the different times, right? So we took the 1 difference. It's not here, but we just plug take the first difference, only the ones, right? Then when I is enter, then we have exactly same outputs, right? It's the same the parameter for MA1 and the same standard error, and any other estimations is a log likelihood and any. So please compare in the homework. I suggest to you, please compare the two statements. Yeah, the difference was how did we take the difference? Okay, so the first one, we used a function, using the function to take the difference. But the second one, we didn't take the difference, but we took the difference, is here. So please understand is what's the difference between the two variables. So now we took the transformation, and second step, we take the A shift and PA shift to choose the model. So we chose the MA1 model. And step 3, we estimated the statistics, the parameters. And now step 4, we have to do the evaluate the parameter. You know, is when we discussed the regression model, yeah, we did exactly same thing. Is the estimate the parameter, and what the and at the end, yeah, we did the evaluation. Do you remember the what was the name of that? The residual plot. Yeah, we estimated the residuals. That was the yi minus yi hat. The difference is between the observed value and the predicted value. So take the residuals. The residuals was the estimate of the error in the regression model. So it must be the IID, the normal distribution is a mean equals 0 and the constant variance again. It's the same thing. You know, our goal is to make the white noise. So now we do the diagnostics for the fitted model, even though we chose the MA1 model, and we estimated is how much will be the parameter for MA1. But now, then step 4, we have to evaluate. We have to diagnostics the choose model, right? But is now for the diagnostics is simply I gave you is another the bigger function. It's a ARIMA. The ARIMA can give us is another picture. So because of the picture, because of the plots, I suggest you is another function is ARIMA. The S stands for the seasonality, the season. So the next topic will be the seasonality for the season. For example, the trend of the passengers for using the flight. They have the patterns, right? Because there is the more passengers in Christmas season or Thanksgiving seasons, right? Or even the summer. So it's every summer, it's every Thanksgiving season, there is more passengers using the flight. So that is a seasonality. That is the pattern. So even as many times we have the seasonality, so we have to delete the seasonality because it is another effect in the time series data. So it's ARIMA is bigger than the ARIMA function because we can take care of the seasonality, but we didn't discuss the seasonality yet, but ignore the seasonality. But I just want to simply apply is the ARIMA model is without the seasonality, is using the function is ARIMA. But anyway, I just plug the log, the data. So we have to take the difference using the number of parameters. You know, the options is a little bit different. It's before in ARIMA, yeah, we are using the options name, the order is equal to something. But this case, it just plug the values, the number of parameters is 1 by 1. So simply just plug the 0, 1, and 1, right? So we don't have to say is the order is equal to using the C function. We don't have to do that. But just simply plug the 0, it's a 1 and 1. The first 0 for the AR is how many P, and the second one is the how many difference. And the third one is the number of parameters in the MA section, is MA part. And then it's a no constant again. No constant is equal to, is a true. You know, it's a function by function. The options is a little bit different, right? So it is not easy to memorize. Is every single options for each function. So every single time you have to do the Google. So even though it's at least you have to remember the name of the function, but it's not too hard to memorize the name of the function because the ARIMA for ARIMA model and ARIMA is a seasonal, is ARIMA model function, right? So at least you can remember what is the name of the function. Then simply you just Google, then you can see the exact option for the function. But anyway, let me type using the function of the ARIMA. Then here is the more statistics, right? The reason why here is the iteration because the ARIMA, I think it's not only ARIMA but also the ARIMA function. There is the iteration. It's kind of the computational the calculation using the iteration. It's a converge to the error. I'm sorry, the converge to the correct answers, right? So here is the iterations informations, and here is the MA estimation. How much was the estimation in using the function of the ARIMA? That was is a point negative is 0.7705. It's the same thing, and the standard error was a 0.0341. But from the ARIMA is exactly the same thing here, and probably the sigma square and the log likelihood or AIC is probably is the same thing. So for statistics, additionally, here is the t-value, the test statistic. For the t-value, probably is using the t-distribution. And this one is a p-value from the t-distribution. That means even though it is only negative 0.77, but probably it is not, is equal to 0. But significantly, it is meaningful, right? And additionally, it's more statistics here from ARIMA. The reason why I suggest you the ARIMA is not only more statistics, but also it's because of the picture is this one, okay? So the very first one is the time series plot with the residuals. Here is the residual is exactly same as the residuals in the regression model. The observed one minus the predicted one from the time series model now here. And it is not the residuals, but it is the standardized residuals. So simply we can check here from the model is a 0, 1, and 1. Yeah, can you understand what is the number of parameters? Yeah, it's a no AR, 1 difference, and 1 MA, right? So it is the standard residuals. So here's a band is between -3 and +3. You know, the standardized one means we can think about the normal distribution, because at the beginning, we assume the white noise was the IID normal distribution is mean equals 0 and the constant variance. So simply from the first plot, the standardized residuals is every residuals is between the -3 and +3. Can you remember the values is plus and minus 3? It's between plus and minus 3 based on the normal distribution. And there is a 99.7%. Can you remember the probabilities, right? So it is a good values. Is all of them is between is plus and minus 3. And simply I can see in the middle, right? There is a mean equals 0. So the first picture for the standardized residual is looks good. It looks like the white noise, because you know we want to make the white noise. And the second one is the A shift. You remember what was the A shift stand for? A shift was the auto correlation function, but for whom? For the residuals. What should be? What should be the residuals? It must be the white noise, right? So we want to evaluate, we want to diagnostics if the residuals are the white noise, the normal IID, the normal distribution, mean equals 0, and constant variance. So now it's A shift, the autocorrelation is among the residuals. As everything is almost in the band. What does it mean? Independent, right? Yeah, from the A shift, the autocorrelation function of the residuals. But even though in number 1 is H, the lag 1, is H equal 1, absolutely it didn't show us is how much will be the A shift at 0. It must be 1. It's always is itself is a 1, is itself, right? But the others, even 1, 2, 3, 4, is everything, is every A shift is in the band. Probably it is a 95% is band. So from the second picture of the A shift of the residuals, we can say the residuals are IID, the independent, okay? And this one is the constant band, the constant standard deviation, right, in the first one. And the third one is the normal is a QQ plot. It's of the standardized residuals. You know, this one is sometimes it's a PP plot or QQ plot. It is the probability plot. So in the middle, the blue solid line, it is exactly the normal distribution. And the circles, that is the residual is from the data. So if the circles is go through the solid line, then you know the residuals, we can say the residual has the normal distribution. So in this case, yeah, it's clearly the circles, the dots, is go through the lines. So simply we can say, it is good enough. It is good enough. The residual has the normal distribution. So using the three pictures, we can say it's IID, independent. It's identically independent from here. And the normal distribution is here. And also the roughly is a mean equal 0 and the constant variance. So it's based on the first three pictures. It looks good. The residuals is the white noise, but the problem is the last one. Yeah, please look at the last one. It is even we can do the test. Even we can do the test. I think is I don't know what is the nationality for this name. Maybe it's a French or I don't know. You can Google. It's a John Box. They suggested the testing procedures. So using their statistic, and this one is the p-value is a picture. So when you look at the p-values, it's very small. When the p-value is very small, what will be the decision? If the p-value is less than 5%, probably the blue, the dashed line is the reference line at 0.05, is 5%. So is all p-values is less than 0.05. You know, usually when we are doing the test, if the p-value is less than 0.05, then we reject the null hypothesis. That is a good one. That is exactly what we want to do. But here, it should not. It should not is less than 0.05. So is the others, the standardized residual plot, or A shift of the residual, or even the normal QQ plot, is everything looks good. But the problem is the p-value. Is a p-value must be bigger than 0.05. So let me show you something. You know, let me show you. Is make the data is another data using the ARIMA sim, ARIMA.sim. Just a second, I cannot remember the statement. Can you, anybody can remember the statement using the, I will show you. Yeah, I'm so sorry. I cannot remember exact the number of I mean the exact options for the simulation one, because you know, anyway, the p-values must be bigger. It's much bigger than this one. So I think for this data, the above one, we have to do is some other things. So let me try, even though we chose the MA1, but let me try is an AR1 model. Yeah, it's no reason. I just try. It's AR1. See, you know, even though I'm trying the AR1 model, this one is a little bit it's a bigger, it's an A shift, right? But still the this picture looks good and normal distribution, and still there is a very small p-value. So it is the problem. So today we discussed how can we use the functions, the A shift 2 or ARIMA function or S ARIMA function, and also I gave you is another data. I cannot remember exactly the name of the data. The second one. So please try again. Yep, it's many of you, it's most of you email me the homework number 14, but today I will give you another one. But anyway, please try the second one, or please look at the diagnostic. It's a picture, this one, for the second data, and please check the p-values, right? So all p-values must be much higher. It's not this one. It's less than 0.05. It is not a good sign. So we have to do more. So sometimes it's in this case, we chose the MA1, right? But it's sometimes we just plus and minus is one more as a parameters, right? It's adjust a little bit. How many P, how many Q, and how many differences, right? Then as always, we do the diagnostics and we just choose the best one, okay? So today is after this meeting, I will email you another um, homework. So you can try one more time, and please understand the 4 steps. The step number 1 is the modification, the transformation, right? It's a log transformation or take the difference. Is roughly the time series plot must be looks like the white noise. It's just white noise. And the second step to estimate the parameters. The second step is the estimation. And the third one is just a second, transformation. And the A shift, PA shift, yeah, I'm sorry. The second step was the A shift, PA shift to choose the model. It's how many P or how many Q. And the third one is the estimation. And the number 4 is the diagnostics, right? So, and then, it's actually the forecasting. Forecasting is a step 5, right? Because we choose we finish up the feeding the model. We chose the best of the best, and then we do the forecasting is based on the best model. So today I prepared another homework and emailed you, and please try again. Probably the final exam looks like this. So I will give you some other examples. Then you do the transformation and the A shift, PA shift to choose the model, and estimation, and the evaluation, the diagnostics, and the forecasting, the 5 steps. So I will give you another homework. This week is the last week, right? So when I finish the lecture this week, and I will email you is about the final exam. So if you don't have any question, you can leave and have a nice day, and see you again on Wednesday. Or if you have any question, please unmute and ask me. Is another just a second. Today, I didn't make the record for the Zoom meeting, but when I'm trying, is here, now I'm recording. So now I will post this meeting again, so you can watch the video again at YouTube. But if you have any other question, email me, or even you can do the Zoom meeting is personally. It's you and I. Sometimes if you have any question, it's not only this homework but also the previous one. So definitely, you can do the Zoom meetings personally. But please you look at the YouTube video first. And still you confused, is any other question, email me. But still it's not helpful, then absolutely you can do the Zoom meeting personally. Yep, have a good day.
Dr.